Hey there, amazing people. I'm thrilled to have you here today. Welcome to our video on multiplicative inverse. We're thrilled to have you here. Reciprocation geometry. In mathematics, our multiplicative inverse or reciprocal for a number x, denoted by x or x, is a number which when multiplied by x yields the multiplicative identity, 1. The multiplicative inverse of a fraction ab is b. For the multiplicative inverse of a real number, divide 1 by the number. For example, the reciprocal of 5 is 1/5 or 0.2, and the reciprocal of 0.25 is 1 divided by 0.25, or 4. The reciprocal function, the function facts that maps x to x, is one of the simplest examples of a function which is its own inverse at involution. Multiplying by a number is the same as dividing by its reciprocal and vice versa. For example, multiplication by or 0.8 will give the same result as division by or 1.25. Therefore, multiplication by a number followed by multiplication by its reciprocal yields the original number, since the product of the number and its reciprocal is 1. The term reciprocal was in common use at least as far back as the third edition of Encyclopaedia Britannica 1797 to describe two numbers whose product is 1. Geometrical quantities in inverse proportion are described as in a 1570 translation of Euclid's Elements. In the phrase multiplicative inverse, the qualifier multiplicative is often omitted and then tacitly understood in contrast to the additive inverse. Multiplicative inverses can be defined over many mathematical domains as well as numbers. In these cases, it can happen that then inverse typically implies that an element is both a left and right inverse. The notation f is sometimes also used for the inverse function of the function f, which is for most functions not equal to the multiplicative inverse. For example, the multiplicative inverse is the cosecant of x, and not the inverse sine of x denoted by or. The terminology difference, reciprocal versus inverse, is not sufficient to make this distinction, since many authors prefer the opposite naming convention, probably for historical reasons. For example, in French, the inverse function is preferably called the. As we venture forward, let's take a closer look at examples and counterexamples and its impact on our understanding. In the real numbers, 0 does not have a reciprocal. Division by 0 is undefined because no real number multiplied by 0 produces 1. The product of any number with 0 is 0. With the exception of 0, reciprocals of every real number are real, reciprocals of every rational number are rational, and reciprocals of every complex number are complex. The property that every element other than 0 has a multiplicative inverse is part of the definition of a field, of which these are all examples. On the other hand, no integer other than 1 and has an integer reciprocal, and so the integers are not a field. In modular arithmetic, the modular multiplicative inverse of it is also defined. It is the number x such that this multiplicative inverse exists if and only if a and n are coprine. For example, the inverse of 3 modulo 11 is 4 because the extended Euclidean algorithm may be used to compute it. The Sedenians are an algebra in which every non-zero element has a multiplicative inverse, but which nonetheless has divisors of 0, that is, non-zero elements x, y such that x is 0. A square matrix has an inverse if and only if its determinant has an inverse in the coefficient ring. The linear map that has the matrix with respect to some base is then the inverse function of the map having it as matrix in the same base. Thus, the two distinct notions of the inverse of a function are strongly related in this case, but they still do not coincide, since the multiplicative inverse of x would be x, not x. These two notions of an inverse function do sometimes coincide. For example, for the function fax xi ion x, where lane is the principal branch of the complex logarithm and exe. Fax ion x ion xi lane xx. The trigonometric functions are related by the reciprocal identity. The cotangent is the reciprocal of the tangent. The secant is the reciprocal of the cosine. The cosecant is the reciprocal of the sine. A ring in which every non-zero element has a multiplicative inverse is a division ring. Likewise, an algebra in which this holds is a division algebra. As we enter this new phase, let's analyze complex numbers from different angles and evaluate its significance. As mentioned above, the reciprocal of every non-zero complex number nearby is complex. It can be found by multiplying both top and bottom of z by its complex conjugate nearby and using the property that z, the absolute value of z squared, which is the real number. A frac is our frac bas bo z our frac bas our frac b plus bar frac plus frac by I. The intuition is that a frac bas gives us the complex conjugate with a magnitude reduced to a value of 1, so dividing again by z ensures that the magnitude is now equal to the reciprocal of the original magnitude as well. Hence, a frac is our frac bas in particular. If z has unit magnitude, then z. Consequently, the imaginary units have additive inverse equal to multiplicative inverse, and are the only complex numbers with this property. For example, additive and multiplicative inverses of r and, respectively. For a complex number in polar form, the reciprocal simply takes the reciprocal of the magnitude and the negative of the angle. A frac is our frac her lefkus of r phi plus is in of r phi right. The time has come to unravel the secrets behind calculus and gain a deeper understanding. In real calculus, the derivative of a is given by the power rule with the power a frac x equal x1 equal x equal a frac x. The power rule for integrals Cavaliere's quadrature formula cannot be used to compute the integral of x, because doing so would result in division by 0. In frac x a frac plus c instead the integral is given by int e frac x lane in frac x lane x plus c where lane is the natural logarithm. To show this, note that our frac d equal e, so if x e and y lane x, we have a beginner leadnid our frac c equal x quadritera quad frac x equal d quadritera quad and frac x int d equal y plus Celsius lane x plus kenda leadnid. As we embark on the next leg of our journey, let's unpack the layers of algorithms and examine its core elements. The reciprocal may be computed by hand with the use of long division. Computing the reciprocal is important in many division algorithms, since the quotient ab can be computed by first computing erb and then multiplying it by a, noting that fax xb has a 0 at x equal erb. Newton's method can find that 0, starting with the guesses and iterating using the rule x n equal x n frac fax nx n equal x n frac x n bx n equal x n x n equal x x n. This continues until the desired precision is reached. For example, suppose we wish to compute 0.0588 with 3 digits of precision. Taking x equals 0.1, the following sequence is produced. X equals 17, 0.1 equals 0.03, x equals 17, 0.03 equals 0.0447, x equals 17, 0.0447, 0.055, x equals 17, 0.055, 0.0586, x equals 17, 0.0586, 0.0588. A typical initial guess can be found by rounding beta nearby power of 2, then using bit shifts to compute its reciprocal. In constructive mathematics, for a real number x to have a reciprocal, it is not sufficient that x 0. There must instead be given a rational number r such that 0 are x. In terms of the approximation algorithm described above, this is needed to prove that the change in y will eventually become arbitrarily small. This iteration can also be generalized to a wider sort of inverses, for example, matrix inverses. As we move forward, let's uncover the untold stories and fascinating intricacies of reciprocals of irrational numbers. Every real or complex number excluding 0 has a reciprocal, and reciprocals of certain irrational numbers can have important special properties. Examples include the reciprocal of E0.367879 and the golden ratio's reciprocal 0.618034. The first reciprocal is special because no other positive number can produce a lower number when put to the power of itself. Phi is the global minimum of facts. The second number is the only positive number that is equal to its reciprocal plus 1. Its additive inverse is the only negative number that is equal to its reciprocal minus 1. The function of an equal n certain nin gives an infinite number of irrational numbers that differ with their reciprocal by an integer. For example, f is the irrational cert. Its reciprocal $1 2 cert is minus $2 cert, exactly 4 less. Such irrational numbers share an evident property. They have the same fractional part as their reciprocal, since these numbers differ by an integer. The reciprocal function plays an important role in simple continued fractions, which have a number of remarkable properties relating to the representation of both rational and irrational numbers. Prepare yourself for an in-depth analysis of further remarks in this section. If the multiplication is associative, an element x with a multiplicative inverse cannot be a zero divisor. X is a zero divisor if some noms are y. To see this, it is sufficient to multiply the equation by the inverse of x on the left, and then simplify using associativity. In the absence of associativity, the Sedenians provide a counterexample. The converse does not hold. An element which is not a zero divisor is not guaranteed to have a multiplicative inverse. Within Z, all integers except 0, 1 provide examples. They are not zero divisors, nor do they have inverses in Z if the ring or algebra is finite. However, then all elements which are not zero divisors do have a left and right inverse. First observe that the map must be injective, implies I begin lean ax I quad ax I equal and quad ax y equal and quad x y equal and quad x equal I and lean distinct elements map to distinct elements, so the image consists of the same finite number of elements, and the map is necessarily surjective. Specifically, namely multiplication by must map some element x to 1, so that x is an inverse for A. Brace yourself for a deep dive into applications as we explore its impact and relevance in our evolving narrative. The expansion of the reciprocal in any base can also act as a source of pseudo-random numbers. If Q is a suitable safe prime, a prime of the form it1 where P is also a prime. A sequence of pseudo-random numbers of length Q1 will be produced by the expansion. I appreciate your time and I'm grateful for every like, comment, and share.